of sequence. Right? So the first thing is what we were up to till now is given a point. You are looking at the functions evaluated at that point and whether that converges or diverges. All right. So let me define a notion. That notion, which is pointwise convergence. A sequence of functions Fn on a set E, which is subset of R, is said to converge pointwise if for every x in E Fn x, the set of real numbers, the sequence of real number converges pointwise to a function f. If for all x in E, the sequence of real numbers Fn x converges to fx. Alright? So what does it mean in terms of epsilon delta? That is, for each x and for every epsilon greater than 0, there exists n depending on n belongs to n a natural number n depending on epsilon and x such that mod of Fn x minus fx less than epsilon for all n greater than, let me put it in naught. All right. So this is what I wrote. Is nothing but, yeah, so if somebody is writing something, I can't see it. So please speak up.
Yes, I was just asking. I mean, I couldn't make out what you had written. Converge pointwise to a.
To a function.
Okay.
To a function f. To a function a. To another function. Or maybe same. So this one is nothing but the convergence of real numbers. This is nothing but convergence of the real number. I incorporated x and this m naught, which will depend on epsilon and x, both of them. All right. So last time we have seen examples. For examples, let me go back to the example 1. Fn x equal to x to the power n on 0, 1. Right? So this converges pointwise. Alright? So this Fn converges pointwise to f, where if x is 0 on close 0 to open 1 and 1 at x equal to 1. Alright? So you check with epsilon delta, epsilon and n, it will definitely satisfy what I said here. So that is an exercise to check in terms of epsilon and n to get more comfortability with epsilon. And now x is coming into the picture, no? So you should be more comfortable with epsilon delta, epsilon n and x. So check with epsilon and n that this Fn converges here. Example 2 here is a different, same example. X to the power n on, let's look at it at minus 1 to 1. Right? Does it converge pointwise?
Yeah, it,
So yeah,
no.
-1 it us.
It does not convert at -1.
Yeah. No, does it converge pointwise?
No, at a lot of points it
No.
won't. I mean, at every point less than 0.
No, I didn't get what you were saying. Every less than 0?
It won't converge if x is between -1 and 0. Oh, no, sorry. At x is equal to
It
-1.
will
it
not converge in x equal to -1.
Yeah.
Right. It will not converge at x equal to -1 only. It will converge at every other point. So this Fn converges to f pointwise. Well, here right. Fn at, I should say Fn at -1, which is the sequence -1 to the power n does not converge. Hence, Fn does not converge pointwise. Does not converge. All right, is this fine? Is this clear? That it does not converge at -1 only?
Yes.
I have a question.
Yeah, Mirza.
So, sir, if we define a function such f and x such that for every value in the domain of the function there is it maps to a finite value, then the function is pointwise.
Well, yeah. This function is Fn is a function, right? Now, are you talking about sequence of functions or just one function?
Sequence of function. So
Sequence of functions. So you have a countable collection of functions. All right. Now, all the functions defined on the whole of domain. So here the functions are x squared, x cubed, x to the power 4, x to the 5 and so on. These are all functions. This is f1. This is f2x and so on. Alright, all these functions are defined on -1 to 1. There is no problem in that. Right? Now, converges pointwise means you evaluate at one point from the domain and look at every function evaluated at that point. Right? So you get sequence of real numbers. Now check whether this converges. So here, except -1, at all other points it converges. In open interval -1 to 1, it converges to 0. At 1, it goes to 1. And at -1, you have this oscillatory sequence. -1, 1, -1, 1, like that. So is this clear?
Yes, sir. Yes, sir.
All right. Okay, so this is example. So let us look at more examples. So I have rearranged the definition. I hope you have wrote it. You have written it.
Sir, sir,
What question? Yes, yes.
sir, in the definition, in the last line where it's written that fx, fnx minus fx modulus less than epsilon, I mean, that is, I mean, we should add something after that, that it holds for all x in the domain of fn, something like this.
No. It does not hold for all x. For each x, there exists an n naught such that it holds. N naught depends on x. So if you change x, your n naught will change.
Yes, but this property is true for all x in the domain of f, isn't it?
Of course, but then this property is not true. This n naught is not same. This n naught will not be the same. So the statement will change. So for every x, you have a different statement.
Okay, sir. Okay, sir.
Right? For every x, this n naught depending on the n naught will change. N naught depends on epsilon and x also. So if you remove this part, and if you remove x here, n naught just depends on epsilon, and if you say this is true for all x in epsilon, all x in the domain, that is a stronger form of convergence. We'll come to that. We are going towards that.
But in this case, that holds, isn't it? Because if for every x we have one n naught, then we also have one n which is greater than these all n naught, for which this property will hold for all x.
No. This n naught can converge can go to infinity, right?
Oh, okay. Since we have infinite number of points in the domain, so this maximum thing may not work. Okay, sir. Thank you, sir.
Right. For finitely many points, your argument is true. Yeah, you'll get a single n naught which will work for every point. Let's look at the following. Example 3. If an x is x plus 1 over n on, let's say, on R. Does it converge?
Yes, sir.
Yeah, it converges. It converges to x, right? X, fx equal to x. So fn converges to x. So see, the difference between this example and this example, right? So this, I said, whenever I write this point or converges pointwise, those who are not comfortable with, not yet comfortable with epsilon and n, please check this in terms of epsilon, n, and x, and see this actually works. All right, so look at this difference between these two examples, right? Example 2 and example 3. So example 2, example 3. In this case here, f and x on the extreme end on 0, 1. So this f and
Excuse me, sir.
is continuous. Yes.
Sir, in the third example,
Yes.
can you please show that how it will converge to fx equals to x when x equals to maybe 0 or lies between 0 and 1?
No, it is fx is x, right? You write this one. You write mod fnx minus fx, right? So what will be this? X plus 1 over n minus h. So this is 1 over n.
Oh, okay, sir. I got it. So I had read the n as x. That is why the mistake occurred.
Right. So what do you need? So you choose given you are given an epsilon greater than 0.
Yes, sir.
And you need to choose a capital N.
Yes,
Right.
sir. We can always choose a capital N such that 1 by n is less than epsilon.
Right. So this is less than epsilon for all n greater than capital N. Really not. So that's it.
Yes, sir. Thank you, sir.
All right. So look at this one. These functions are continuous. So fn is continuous for all n. And here also. We erase this part. This is very simple. So in example 3 also, f and x is x plus 1 by n is on you could take r or you can take interval 0, 1, doesn't matter in this case. So this here also fn is continuous for all n. Now this fn converges pointwise. This fn here also converges pointwise. All right. Now, what is the limit? Here, limit function. The limit function is not continuous, right? What is the limit function? Limit function is limit function f x is, as I wrote that side, 0 on 0, 1 and 1 on 1 at x equal to 1. This is not continuous. In this case, the limit function is continuous. So this is a difference, right? This is a difference. Continuity is not preserved under pointwise convergence. All right? Is it clear? At some functions it may be continuous, some functions it may not be continuous. Let us look at more examples. All right. So here you could change change this example a little more. Any polynomial where Px is a polynomial in X. Alright. So Fn you converge to P pointwise. Yeah, let us do more examples. Even more. So you look at this one. Fnx equal to x square for mod x less than n, and this is n where x less than equal to bigger than n, minus n when x less than minus. All right, this is another example. So look at, if you want to look at the picture, you can look at. So this is the x-axis, this is y-axis, fx. And for example, for f1, you have this minus 1 to 1. You have y equal to x square. So you have this. And at this is 1, and at minus 1, and this is minus 1. Here it is like this, and like this. So this is F1. So this is F1. Let us look at another one, F2. You have this minus 2 to 2, and this is 1, this is minus 1. So minus 2 to 2, it will be And from 2 onwards, right, and from -2 onwards, it will be here. All right. This is fine. Looks fine. And as you move -3/3, it will be y equal to x squared from -3 to 3, and then oh no, this is m, so it will be here. Sorry, it will be 2 here and -2 here. Yeah, now it makes sense. Right, I was thinking, if this is 1, how can this be 4? So a little bit. Now this seems good. This is 2. So from 2 -2, less than -2, it is 2, and greater than 2, it is -2, and greater than 2, it is 2. And similarly for F3, you have -3 to 3, y equal to x squared, and after 3, it is 3, and less than -3, it's again -3. All right. So does it convert pointers? Anybody? Is the connection lost or what?
So yeah, it should converge pointwise to f of x is equal to x squared.
Right. Right. It converges pointwise to x equal to x squared. Yes. Because you choose a point, after some name, you will get that equal to x. Whatever x you choose, you will get that value of fnx to be x squared after some name. Right? So after some n, you get x squared, x squared, x squared, x squared, x squared, and so on. So it converges to x squared. So this Fn converges to a pointwise, where fx equal to x squared. Example 6.
Sir,
Yes.
I quite don't understand how it converges to x squared. Can you explain it again?
Yeah, so is the picture clear to you?
Yes, sir.
So look at the picture. This parabola is same, right? We are cutting the parabola at -1 and 1. Here we are cutting a parabola at -2 to 2. And at the third stage, we are cutting the parabola from -3 to 3, right? Let me draw the picture again in a single picture, not in a multiple picture. So you have this. So here it is -1, -2, -3, -4, 1, 2, 3, 4, 5. So you forget about this part at this point, because this part is moving. As n tends to infinity, these are going towards infinity. They are moving outside minus into n. All right. So what we are doing is we are cutting the parabola at -1 to 1 first. At the second stage, we are cutting at -2 to 2. At the third stage, you are cutting -3 to 3, and so on. Right? We are cutting there. And outside there is whatever this number, it's defined. So now you fix a point. So fix a point. Well, this is not example 6 now, it's still going on. So fix the point x in where? Now, right? So there exists n naught natural number such that mod x is less than n naught. Is this correct?
Yes, sir.
All right. Now, what is fnx minus fx? Right, which is for all n bigger than n. Look at for all n bigger than n naught, this one. What is this?
It's 0.
Right, so for this point, fix a point, so let's put it x naught. Is 0, right? Which is less than epsilon. For every epsilon. Right? So this is less than epsilon. But you see here, this n naught depends on x. X naught you have chosen. Alright? It's very clear.
Okay, sir. Yes, sir.
So this is 0, so it converges. So if an x naught converges to f of x naught, and this point was chosen arbitrarily. Right? I'm not writing everything, it is difficult to write this board, everything in this board, and of course, it is not the aim of the course also, you should cover the gaps up. But since x naught was arbitrary, so then this fnx converges to fx for every x now. Alright now? Yeah, any other question?
No, sir, I understood.
Alright. Alright, so let's look at another example. Example 6. Here I can draw the graph. So this is limit fn x is defined as that. Limit n tends to infinity cos factorial n by x to the power m. Do you see? Is the definition clear?
Yes, sir.
Cos factorial n, this n is same as this n, pi x equal to the power n, and this limit n goes to infinity. Alright? So practically, when factorial n x is an integer, you get 1 and otherwise 0. Right? Cos of whatever is mod less or equal to 1, right? Mod is equal to 1 where it's n pi. Right? Yeah, are you scared with this, looking at this example?
No, sir. If the cos, I have doubt. If the cos n pi x value is -1, then the limit is not defined, right?
Cos n pi x is,
If cos n pi x is -1,
oh no, this is not n pi, it's factorial n.
oh, okay, sir.
It's factorial n. So it is always 2 pi, 2 is there always. So we are looking at even number only. So the point is when n factorial n x is an integer, right? Then we get, well, even integer actually.
When x is rational, the function converges to 1. When x is irrational, it converges to 0.
Right. So then we get that, but you need to look at the function first, right? What is fn x? So when this is an even integer, you get fn x in 1. Right? But can it be an odd integer?
Sir, is this function a formal way to write down the Dirichlet function?
Well, this function is this function converges to Dirichlet function.
Yes, sir. So, sir, suppose we write it in this way, limit, suppose we write the Dirichlet function in this way, limit n tends to infinity, m tends to infinity, cos n factorial pi x all to the power n.
Right.
So, it will be a formal way to write down the Dirichlet function.
Right. So yeah, this one you look at when it is 1 at some point, otherwise it is 0. So let me go into the limit since you already
Sir,
yeah. Limit
if cos n factorial pi x is negative, then will it will the limit exist?
right. So that is the question. That is the question I was asking. So when it is factorial n times x, negative doesn't matter. The point is when it is odd integer, right? So what is cos pi?
-1.
-1, right? So there will be that problem. So that problem has to be removed. So here, let's look at f1. F1, you have pi x, then you need to look at you look at this one on right, then you have at 1 cos pi. Cos pi is -1 and you have whole to the power n, right? Well, here what you want to do is you make it 2n. That corrects it, right? Is this fine? So
Yes,
there can be minus sign, but then if you put here 2m, then it corrects it. It gets corrected.
I didn't understand what the problem was with just m.
The problem was, for example, f1, right? What was f1 earlier?
Cos pi x to the power m.
Right. What is the value at x equal to 1?
It's -1.
How?
No, cos pi, right?
Yeah, 1 to the power m as limit n tends to infinity. What is the value?
Oh, okay. Yeah, that
F1.
would convert.
That is the problem. But fnx has to be a function, right? So that should be corrected, and putting a q here corrects that. Right.
Sir,
Yes.
to delete the negative values means, are we doing that to stop the oscillation, right?
You need to get a function. So define a function properly, right? Fnx is not a function if you remove this one.
Okay.
Right? At some values it has at some points it has no value. No convergent. I mean it's this as n tends to infinity, you don't get limit. Alright. So now this Fn converges f pointwise where fx is 0 when x is irrational and 1 when x is rational. Is this clear? Is this clear? That this converges to f, where f is 0 at irrationals and 1 at rationals.
Sir, can you explain the irrational part? I mean, how?
So when you have x to be rational, right? P by q. Right? When x is p by q, you look at n bigger than q. What is factorial in x? This is an integer, right? This belongs to z. All right. So you get the value 1 at p by q after for all n greater than q, right? Hence it converges to 1 at p by q at x equal to p by q. All right.
Yes.
Yes, sir. And what happens if x is irrational? How are we concluding it is 0?
Yeah, because it's not a 1. It's cos. The value of cos is not a 1, neither -1. Right? Where does that belong?
Okay, so then it really is converts to 0. Yes.
Right? So it belongs to open interval -1 to 1. Now any such number for m goes to 0. So the value of the fn itself is 0.
Okay. Yes, sir. Got it.
Correct? Okay. So So here the explanation is given to you, and if you want to look at more explanation, you can look at Rudy's book. This example is from Rudy. But what my point is, you see, pointwise limit can be discontinuous everywhere. Of course, it has point of discontinuity as well. But this can be anything. So the point is that the question is now that under what condition the limit of a convergent sequence will be continuous given the sequence is continuous. So under what conditions limit of continuous functions is continuous? Right? You get the question? Question: under what condition the limit of a sequence of continuous functions is continuous? Right? This is the question. You want the limit sometimes, right? So most of the cases you pass through the limit and you want the limit to be continuous as well. So here we need a stronger notion of convergence. And that is uniform convergence. A sequence, so this is the definition, a sequence of functions Fn is said to converge uniformly to F if for every epsilon greater than 0 there exists n naught belongs to n such that depending on epsilon only, such that mod of fnx minus fx less than epsilon for all n bigger than n naught and for all x v. So the set is C. sequence of functions fn on set E. So here this n naught depends only on epsilon. It does not depend on x, and this works for every x. This works for every x. Is this clear? Is this visible?
Yes, sir.
Can you
I didn't get the question, Shobik. Please repeat what you want to ask.
Yes, sir.
Sir?
Yeah. So this is visible, right? Clearly?
Yes, sir, it's visible.
Okay. Yeah. Any question?
Sir, so if a function is uniformly convergent, it will be pointwise convergent, right?
Yes. Yes. Because this is for every x, this is true, right? So it will definitely be pointwise convergent. So this is a strong version of convergence.
Okay, sir.
All right. Example we have given already. So example 7 here. Fnx equal to x plus 1 over n. 1 half. This converges uniformly. Fn converges to f uniformly. Where fx is x. Instead of x, you look at any polynomial, this also converges uniformly. All right. But exercise is that show that fnx x to the power n on 0 to 1 does not converge uniformly. All right. So you get the negation of it. I think you know how to do a negation, right? Do you know that? Yeah.
Yes, sir.
Okay. So get the negation of it, and so using that, so that this the sequence this fx equal to fnx equal to x to the power n does not converge uniformly. All right. So this will be part of the assignment, which will be uploaded by this weekend. You all right? If you have any question.
Sir,
Yes.
so the basic difference between pointwise convergence and uniform convergence is that in pointwise we do not specify that the function should be the same for the entire domain. The function that it converges to may or may not be same for the entire domain in pointwise. Whereas in uniform convergence, we say that it should be the same for the entire domain.
No. The difference lies here. The difference lies here. So what is the difference? Difference is that same n naught works for every point x in the entire domain. So both the cases you have limit. There is no problem in that. In the whole domain you have limit function for pointwise convergence as well as for uniform convergence. All right. The point is that the how the limit behaves. Well, how the sequence behaves around in the neighborhood of the limit, in some sense. Your question is very good, and that depends on here. This is very crucial. This point. What is the difference? Difference is this n naught, which comes in the definition, which works for every x. On the other hand, in the pointwise limit, you have this n naught depending on x. As x changes, your n naught will change. In this case, this n naught will not change. So the point is, yeah, so maybe I'll draw a picture. That might clear doubt a little bit. And next time we'll show that uniform limit is continuous. Uniform limit of continuous function is continuous. Answering the question. So suppose this is a function or interval. Suppose this is function f1. So it might happen that something like this can happen, and let's say right, so you have these functions f1, f2, f3, f4, so the point is that, and suppose this becomes the limit. So the point is, in this point, at this point, what is convergence? This is, you look at a small neighborhood of this graph, however small you want. That is the epsilon, right? So this part, this is epsilon, right? And this white picture should come into this picture, into this neighborhood. So the point is, here at one point, it might become after. So this is f1. Like this, it can jump for pointwise convergence. At some point, you have after sudden, let's say after 1000, it falls into there. At some point, it falls into after 1 lakh, and so on. After a year, let's say it falls into certain 1 million or 1 million or 1 million or 1 billion. It might happen, but the uniform convergence would be that if it works for one n here, it should work for every n. So if here the whole graph will lie in this case, in case of uniform. Yeah, maybe. So this one pointwise. Maybe I'll draw this yellow. So in case of uniform, the whole graph must lie in it. And there you might not get the whole graph that will lie in the neighborhood. Do you see the difference?
Yes, sir.
It's actually a little complicated to appreciate, but I'll suggest you think of this one, draw this picture again, try to think what is uniform and what is pointwise convergence. This difference, understanding this difference is very crucial for this chapter, even for this whole course. And your question was very good because I got a chance to explain. I forgot this to explain. I really remember that I have to explain this. But this is important. The whole graph might not lie in a Epsilon neighborhood for pointwise in convergence case. But for uniform, after some n, the whole graphs must lie.
So it basically means that if we draw a vertical line x equal to some c, the whole y points that will be there in that line will come into an epsilon neighborhood that we won't get in a pointwise convergence.
The vertical line here it's not about vertical line, right? So if you draw a vertical line, what happens? Vertical line is not a graph. So what the point is?
No, I'm saying that the y points on that line, if we draw suppose x equal to c, where c belongs to our line, so all the y points that are in that line, I mean,
all the points might not be in some graph, but the point is the graphs which are closer to here, the whole graph must lie in this neighborhood. So you see this blue one. This blue one is a neighborhood. Is the neighborhood. Right? This blue one is a neighborhood. And after some n, the graph of Fn must lie in that neighborhood.
Okay. So basically, the f values after a certain n become concentrated in an epsilon neighborhood.
Concentrated and on this epsilon neighborhood of whole graph at every point.
So in pointwise convergence, we won't have that. Okay.
Pointwise convergence, you don't have. At some point, it might be close. It might be another point. It might not be closed. So you might not get an n after that. It will be concentrated here. This may not happen.
Okay, sir.
All right. Okay. So next two class I'll be using iPad, and you will decide then which one is better, board or iPad. So which one you prefer, let me know. Okay. And then we'll go with that one.
Sir,
Yes.
I have a question.
Yes, sure.
In case of sequence of function, in case of uniform convergence, is the limit of the sequence of function will be continuous?
Limit of the sequence of functions whose members are continuous, right? So continue the limit of uniform limit of continuous functions. So Fn are continuous for all n, will imply the limit will also be continuous. So that's what will be. This is the main theorem of this chapter.
Okay, sir.
The next time we'll prove that. All right. And I have uploaded a chapter on sequence and series of functions. Okay. So examples mostly are taken from there. And this is very easily written, so you can read that one as well. And by this weekend, you will get the notes for this week. All right. See you then. Bye.